Hello and good morning, students. Today we're going to continue with the next objective. Yeah, we have covered the first bullet here, how the resting potential is maintained. Okay, so remember there are two ways or two important points uh, in which the resting potential is maintained. The first one is the different permeability of the membrane of the axon to sodium and potassium, and number two, the action of sodium potassium pump. Okay, now the next one today we're going to look at these two bullet points here, if we have the time as well to do the last bullet point here. The second one is the events that occur during action potential. So we have covered resting potential. Now we're going to look at the event that occurred during an action potential, and then how the resting potential is restored during the refractory period. Okay, let's go straight to the action potential. So action potential, before that, a nerve impulse or electrical impulse can be initiated by anything mechanical like pressure, or chemical, or it can be thermal, or it can be electrical stimulation. So for instance, when a small electrical current is applied to an axon, the resting potential changes, and these are only temporary. So it will switch from minus 70 millivolt to plus 40 millivolt. Okay, so now the inside is higher by 40 millivolt compared to outside. So just by looking at these figures here, when we say minus 70 millivolt, this is resting potential. We say that this the inside is 70 millivolt lower than the outside. Okay, that's the meaning of it. So if it's plus 40 volt, it means that the inside is 40 millivolt higher. The inside is 40 millivolt higher than outside. This means that the inside of the axon becomes more positive, and you should know that how it becomes more positive, because the entry of sodium ions, and the outside becomes more negative. This is called the action potential, which will last about 3 milliseconds. So it's very, very temporary. So action potential is the change in the potential difference. Change in the potential difference across an axon membrane, which occurs during the passage of a nerve impulse. There is a temporary reversal, minus 70 millivolt plus 40 millivolt. So that plus 40 millivolt is only temporary of the resting potential, so that the inside is positive compared to outside. So what do we mean by inside more positive? It means more positive ion, more positive ion on the inside, less positive ions on the outside. Okay, it's only temporary. Action potential only occurs in one small section of the membrane at a time. Okay, a nerve impulse consists of movement of or propagation of an action potential along a nerve axon. So just in a nutshell, in a non-myelinated neuron, regardless if it's motor neuron or sensory neuron. Here I give you an example of a motor neuron. Okay, something like this with the nucleus. So if this is the direction of the action potential or nerve impulse, so this area here becomes positive, negative, 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 positive, positive. So action potential, if this is action potential, occurs in the initial part of the cell body here. Let's say this is the cell body. There's a stimulus here coming from the previous motor neuron. So inside now becomes positive, outside becomes negative. Okay, and so this will continue. Yeah, this will continue. It will propagate. So the meaning of propagate Propagate means it moves along. It moves along this axon. So the next one would be that this one will become positive, this one becomes negative, this one goes back to negative, this one goes back to positive. Okay, so this one becomes negative, this one goes back to positive. Okay, and then it will propagate to the next one here. So this one will become positive again, this one becomes negative, yeah, and this one will return back to negative, this one becomes positive. And then this part area here will become positive again, negative, and then this one will go back to negative, positive, positive. Okay, and this goes on until it reaches the end of this neuron, and then we'll connect again to the next neuron, and finally to the effector. So this is in a non-myelinated neuron. In a myelinated neuron, it's different. So in a myelinated neuron, okay, so in a myelinated neuron, because of the presence of the node of Ranvier, so it will jump. Yeah, so I'm just gonna make something like this. Okay, so if this is the node of Ranvier, okay, this one as well. So if this is positive, negative, negative, so action potential occurs here. This is still negative, negative, positive, positive. Okay, so what happens is that this will jump, yeah, the positive here will jump like this. It's not literally jump, yeah, we call it saltatory conduction. Saltatory, I've been mentioning this all the time, saltatory conduction, but it's not literally jumping, it's just like it's faster, yeah, it's faster. So this one will be attracted, we call it the local electrical circuit, we'll talk about it later on. So where positive zone is attracted to negative zone, so this one will become positive, this one becomes negative, yeah, and this one will go back to negative, positive, positive, yeah. So it's called saltatory conduction, saltatory conduction. Okay, so this is in myelinated, this is in myelinated neuron, yeah. In non-myelinated, it has to go through all the regions until it reaches the end of the neuron, and then connects to another neuron until it reaches the effector. Whereas in myelinated neuron, it will jump from one node to the next node. Okay, from one node to the next node. Okay, so that's the meaning of consists of a nerve impulse consists of the movement of propagation of action potential, movement or propagation of action potential along a nerve axon. So this one depending on whether it's myelinated or non-myelinated. When an action potential occurs, the axon is said to be depolarized. So the word D is mentioned here, depolarized. This is during action potential. So resting potential, the axon is said to be polarized. So in action potential, when action potential occurs, it is said to be depolarized. Okay. However, after about 3 milliseconds, the resting potential is re-established and the axon is said to be repolarized. So after, because this is only temporary, yeah, remember action potential is only temporary. Yeah, so it will go back to the state of polarized. So in order to go back to the state of polarized, it is repolarized. It's going back. So eventually, before it's polarized, it is repolarized, and then eventually it will be polarized. So a membrane is said to be polarized if the potential difference is maintained across it with the inside being negative. So polarized here, this is resting, yeah, resting potential. Yesterday's lesson. If inside is negative compared to outside, whereas if it's polarized, then it is the inside now becomes positive with respect to the outside. Okay, this is very, very important. Yeah, very, very important. Now this is the graph of an action potential. So in the exam, this can come out, and they will ask you what's the state of the membrane. Yeah, so this part here is polarized, this part here is polarized, this part here is depolarized, and then repolarized, and then this part here is hyperpolarized, and then this part here is going back to polarized. Okay, so you have to know the reasons behind this minus 70, and then plus 40, and then going down, and then hyper, and then going back again to plus minus 70. Okay, so now the area about minus 55 millivolt here, which is the threshold value. So if you draw the line here, it's about minus 55 millivolts, the threshold value. So if you draw the vertical line until where it becomes minus 70, okay, so this is called the refractory period. Refractory period. Okay, refractory period is like a recovery period. Your syllabus only mention the term refractory period. Yeah, actually in detail there's a absolute and there's also relative. See the importance of refractory period. This also during how the resting potential is restored during the refractory period. So it doesn't mention the two types of refractory period, which is absolute and then relative. So we're not going to go into the detail of this absolute and relative refractory period. I will give you the notes, by the way. But yeah, just to show you where this refractory period is, the refractory period is in this area here, in this part here. Yeah, this is the refractory period from about minus 55 millivolt. Okay, when it's minus 55 millivolt, that's the starting point of the refractory period, which is the threshold. Minus 55 millivolt is more or less about the threshold value. Okay, so what it means is that in order for action potential to occur, it must have enough stimulus. The amount of stimulus must be strong enough in order to in order for the action potential to occur. Yeah, the strength must be strong enough in order for action potential to occur. We'll talk about that later on. Yeah, so the strength is about, the minimum is about minus 55 millivolt, and this is the starting point of the refractory period until it goes back to minus 70. Okay, so it goes back to minus 70. This is minus 70 millivolts. This is plus 40 millivolts, and this is go back to minus 70 millivolt. Okay, now you have to know the reason. So let's just clear this. So you need to know the reason. Now the reason for this part here, this is resting potential. So you have to know the reason of why is this resting potential maintained at minus 70. So remember the two reasons. The first one is the differential permeability of the exon membrane to potassium and sodium, and the other one is the action of sodium-potassium pump. So that is the reason why this is maintained at minus 70 millivolt. Okay, and then why suddenly, when there is a stimulus, suddenly it goes up to plus 40 millivolt? What is the reason here? Yeah, so if I can just use a different color here. So what is the reason behind here in terms of the ions? So in this area here, this is because of the influx of sodium ion. Sodium ion enters. Yeah, sodium ions enters, and so the inside is more positive than the outside. Okay, and then you need to know again the reason behind this area here. Okay, what's the reason here? The reason here is because so it's going back to negative minus 40. So this is the outflux of potassium. Okay, meaning potassium leaves the exon. And now the next one is this one here. Why does it go beyond the minus 70? Yeah. So if you were to measure this part here, this is actually beyond minus 70 millivolt, meaning there's an overshoot there. The term is overshoot. Why? Because this overshoot is because the potassium channels continue to open. It's not closed yet. Yeah, so potassium channels continue to open, so it becomes even more negative outflux of potassium ions. Okay, and then so it's like pressing the brake. Pressing the brake pedal too late. Yeah, it's still taking time. So when the potassium channels are completely closed, then it will go back to minus 70 millivolts. So how does it go back to this minus 70 millivolt? And this is due to the action of the this part here. How does it go back to this? How does it restore back to the minus 70 millivolt? So this is due to the action of sodium potassium pumped. Okay, sodium potassium pump. So if we go back, when we do this graph, you have to understand the resting our yesterday's topic when we talk about the resting potential. Yeah, so we can draw an exon here. Remember, the inside has more potassium, less potassium outside, less potassium. The inside has less sodium, outside has more sodium. Okay, remember we are talking about resting potential. So we say that resting potential is about minus 70 millivolt. How is this possible? The inside is more negative compared to outside. Okay, so basically inside is negative compared to outside. Okay, so why is this the case? Because the sodium, this sodium here, leaves. Okay, so in the resting potential, the potassium, so in the resting potential, the potassium ions leave the exon, whereas the sodium ions cannot enter Yeah, it cannot enter. Cannot enter here. They cannot enter because the sodium channels are closed. Okay, and so the inside is more negative compared to outside because the potassium leave, potassium ions leave the exon. So, and this is how, and of course the action of sodium potassium pump. Now this is in resting potential. So if it's action potential, so in an action potential is the other way around, yeah. So in an action potential, what happens is that, so again, high potassium, low sodium, high sodium, high sodium. So in an action potential, so action potential plus 40 millivolt, what happens is that now the sodium can enter. Okay, the sodium can enter and the potassium cannot leave. It's the reverse. Potassium channels are closed, sodium channels are open, and so the sodium can enter, and that's why the inside now is positive. Outside will be negative. Okay? So the thing is, it's very simple concept. If you want to make the inside negative, potassium has to leave. It's a very way. This is an easy way to understand this topic, yeah? And that is, if you want the exon to be negative inside, the potassium has to leave. If you want the inside to be positive, the sodium has to enter. Okay, sodium has to enter. So if we go back to this slide here, okay, as you can see, this is the resting potential. You should know the reason, the two reason. And then this is positive, plus 40 millivolt. So sodium will enter. Sodium will enter. So after plus 40 millivolt, it's trying to go back to negative now. So now potassium must leave. So out flux. And then it reaches minus 70, but there's an overshoot, yeah? There is an overshoot here, meaning it continues, the potassium continue to leave because the potassium channels are still open. It's like, it is late to press the brake pedal. Yeah, but after it eventually close, the channels, potassium channels eventually close, how does it go back to minus 70 here? That's because of the sodium potassium pump, action of sodium potassium pump. So going back to minus 70 millivolt. Okay, so very, very important, very, very crucial, yeah, that you understand that, because in the exam, this is the sort of questions that they will ask you, reason for each part of this graph, and then the state of the membrane. Is it polarized, depolarized, repolarized, hyperpolarized, or polarized? Okay, right, this is the one that I just showed you just now. So the propagation of the nerve impulse here. Okay, so eventually, when it moves in this pathway, eventually this one become positive, this one become positive, yeah, and the previous positive region will become negative. This one will become negative, yeah, positive, and then and so on and so on and so on, yeah. So what I mean is, if this region is positive, it will make the next one positive, but then the previous region will go back to negative, and so on and so on and so on, yeah. So this is in this case here, this is the propagation of nerve impulse in a non-myelinated, yeah, non-myelinated neurons which are not myelinated. Okay, there are neurons which are myelinated, there are also neurons which are not myelinated, yeah. If a neuron is not myelinated, it does not necessarily mean that it is or the person or the individual is suffering from a disease like multiple sclerosis. Yeah, because there are neurons in our body which naturally do not have myelination. Okay, right. So as you can see here, yeah, this is permeability, yeah, permeability. So this part here, this is where the sodium begins to enter. And you can see the permeability of sodium increases, yeah, in this corresponding region here. Okay? And then going down, so going down here, so if you go down, this is when the potassium begins to leave. And now you can see the permeability of potassium increases. This area here. Permeability of potassium increases because in this region here, potassium leaves the exon. And so on and so on. So that's how it's done. Okay, so events of the action potential. So we can read this one here. Okay, you can read this one in your own time. I prefer to use the graph which I've made myself, like this one here. Is easier. Yeah. So all of these events of action potential, yeah, all these numbers, number 1, number 2, 3, 4, 5, 6, yeah, and 7, 8, it's all been summarized already in the form of this graph here. So it's easier. So I prefer to use this graph. Okay. So the first thing is maintenance, this one here. This is minus 70 millivolt. Okay, I'm just going to write down here minus 70. Minus 70 millivolt. How is this minus 70 millivolt maintained? That is because of these two regions here. The sodium channels are closed, potassium channels are open. Bear in mind, it's not all sodium channels completely closed, and as well as it's not all potassium channels are completely open. So we say most, yeah, we use the term most, but this is just for simplicity purposes. So generally we can say that sodium channels are closed, potassium channels are open, yeah. So and then the action of sodium potassium pumped. Okay, so make sure that you know when we talk about the action of sodium potassium pump. Sodium potassium pump means every time when 3 sodium are pumped out, only 2 potassium are pumped in. Yeah, so eventually 3 positive are removed and put back 2 positive. So eventually the inside will become even more negative. Okay. Okay, and then this part here of the graph, okay, this part here, as you can see, what happens here is that the sodium enters. The sodium, so if you see here, sodium channels or gates start to open, and then the potassium channels begin to close. Yeah, so that's why the influx of sodium becomes plus 40 millivolts. And then the opposite will happen. Okay, this is the opposite. The opposite is sodium channels begin to close, potassium channels begin to open. So I wrote in the previous slide, outflux, the potassium will leave. And now it's becoming negative. And then there is an overshoot here. Okay, there's an overshoot, this overshoot region here. And that is because potassium channels continue to open. It's late pressing the brake pedal, it's still open. potassium channels are still open. And then how does it go back to this normal minus 70 millivolt? Okay, so this is already the normal resting potential, and that is because of the action of sodium potassium pump. Okay, very important. This graph is very important. It's the same like what I have explained using this one here just now. Okay, so if you want to read the events, you can read this two slide here, number 1, 2, 3, 4, 5, 6, 7, and 8. But I've already summarized it in the form of this graph. Okay. Right. So for an action potential to occur, there is a threshold value. Yeah, the threshold value is only about roughly about minus 55 millivolts. Yeah, meaning the strength of the stimulus must be strong enough. It must be strong enough in order for action potential to occur. Okay. So this from the onset of the threshold value here, yeah, this threshold value here, this is the refractory period until it goes back to normal, meaning this is about the resting potential, slightly slightly around that region there. So this is called the refractory period, this area here. Yeah, refractory period. We talk about this refractory period in a moment. Okay. Okay, so here we have the non-myelinated, in a non-myelinated neuron. So as you can see here, so in order for, just look at this area here, in order to make the inside positive, sodium has to enter, and the potassium must be close. These two area here. Okay, so this is a bit misleading, but let me rephrase. In order to make the inside positive, sodium must enter and the potassium channels must close. Yeah, because you want to make the inside more positive ions. Okay. You can check, you can do this in your own time. Yeah, this MCQ. Statement is correct. Action potential, sodium ions rush out, so this is wrong. It should be in. Okay, so A is wrong. Action potential are generated in the dendrites, wrong. They are generated in the cell body. Yeah, the beginning is cell body. Of course, if it's a motor neuron, we will start from a cell body. If it's a sensory neuron, then it's from the receptor. Yeah, so this is depends on the question. Calcium ions are involved in repolarization of the membrane. No, calcium ion is not involved. If the membrane becomes hyperpolarized compared to risk potential and action potential occur, no. The best answer is E. Yeah, the degradation of myelination along an axon reduces the speed at which action potential occur in example called multiple sclerosis. So E is the answer. Okay, E is the correct answer. 39. Why does myelination increase the speed of action potential? That's because of saltatory conduction. So A is the answer here. Myelin insulates the axon from the leakage of ions across membrane, which allow the action potential to hop. Hop means jump. Yeah, jump. This, which is the meaning of saltatory. Yeah? Saltatory conduction. The rest are wrong. So A is the answer. Okay, so the last part of our today's lesson is talking about the refractory period. Yeah, the refractory period. So what is this refractory period? The refractory period is when an action potential has just occurred at a section of the axon. There is a short period of time. So let's read it. When an action potential has just occurred at a section of the axon, there is a short period of time when a second action potential cannot be generated at that same point. Okay, this is called the refractory period. It occurs because the sodium channels are closed and cannot be stimulated to open immediately. The membrane cannot be depolarized and a new action potential cannot be formed. So there are two benefits of this refractory period. It imposes an upper limit on the frequency of nerve impulse, meaning there's only a certain nerve impulse that can be fired per unit time. Yeah, because the refractory period lasts for approximately 4 to 8 milliseconds, it limits the number of nerve impulses that can pass along an axon at a given time. It ensures that nerve impulses can only pass in one direction along an axon. They can only pass from an active region to a resting region. They cannot double back because the membrane immediately behind the active region is in refractory period and cannot be depolarized. Okay. Right. Let me just find the image. Okay, if I can just draw a motor neuron, okay, with a cell body here, nucleus, this is dendrites, okay, this is at the end here, synaptic bulb. Apologize for my drawing here, or knob or terminal. Okay, right, and of course this is the axon here. This part here is the axon. I'm not gonna draw the myelin. I'm not gonna draw the Schwann cell or myelin sheet. So I'm just gonna assume that this is non-myelinated. Okay, so let's use, it's all negative here. Okay, and outside positive. Let me just rub this off here in the space. Positive. So the impulse will come from this direction here because it's from the previous, it's connected from the previous motor neuron. If I can use an example of a motor neuron, so it's the arrival of the incoming the arrival of the nerve impulse is from the previous motor neuron, and so it will synapse in this part here in the dendrites, and then action potential will occur here. Okay, so if an action potential occurs here, can use a different color here. Now this one becomes positive, negative, negative. Okay, and then it will move. Yeah, it will move to the next one. It will move to the next one. This is now positive, negative, negative, and then this will go back to negative. It will slowly, it will try to go back to the previous state. Okay, now if there is another incoming, if there is another incoming action potential, incoming nerve impulse here, then this part here cannot be stimulated. This part here cannot be made positive because this is still in refractory period. Okay. 2 plus. So this is still in refractory period. Okay, meaning you cannot make this one positive for a brief second. If there is an incoming nerve impulse, okay, so technically this one will be made positive, and then it will propagate. But that is not the case because this is still in refractory period. Okay, in refractory period. So what it does is that it allows this one to pass first. After a few milliseconds, this one it will allow to pass first and will reach the end of the terminal at the end of this neuron. It allows this one to pass first. Only then this can be made positive again. So it actually limits. So the purpose of this refractory period, now first of all, why this cannot be made positive? Because of the sodium ions cannot be made to open. So why? Because sodium channels cannot open. Sodium channels cannot open because it is still recovering. It is trying to reset. It's still in the process of resetting. Yeah. So if we look at then the previous what it says here in the refractive period. Okay. Because sodium channels are closed and cannot be stimulated to open immediately. Okay, so the benefit of this refractive period is that it will limit the action potential that can occur or that can be fired along this neuron per unit time. Yeah. So the refractive period means, because this was previously positive, now it will move to the next one. Next one is positive. This is now going in refractive period. And this, if there is an action potential or incoming nerve impulse from here, this cannot be made positive because this is still in refractory period. Okay, and what it does is that it will limit the nerve impulse, the firing or propagation of nerve impulse along this nerve, the frequency of the nerve impulse. It will limit the frequency per unit time. Okay, limit the frequency, and this is very important so that your neurons do not suffer from overstimulation. Your neurons will not suffer from fatigue. Yeah, and you will not burn too much, or you will not consume too much ATP. Yeah, so this is to prevent overstimulation, to prevent the firing of nerve impulse, the frequency, yeah, to limit the frequency. Frequency means number of times per unit time. Number of times per unit time. Yeah. So to limit the frequency of nerve impulse per unit time. Okay, that's the first reason. The second reason is that, so that the nerve impulse will only travel or move in one direction. Okay. So if I can draw another one, I don't want to mess up with my beautiful drawing. Yeah. The second one is, I'm just going to draw the dendrites here. Let's draw a better one. Okay, cell body, this is the nucleus. Okay, so this is negative, positive. Okay, so let us say now the nerve, the nerve impulse is already in this area here. Let us say that here is already positive, negative, negative. Yeah, and this is still in refractory period. Okay, refractory period. Now, because this is positive, okay, positive here. So, how this nerve impulse propagate is because of the positive zone attracted to negative zone. Okay, we'll talk about that later on, but that's how it is. How it moves along this neuron is because of positive zone attracted to negative zone. Yeah. So, if this is already positive, it can actually go. There are two options for this nerve impulse. It can be attracted to this negative zone or attracted to this negative zone, because there are two negative zones here. Okay, so meaning this can go here or it can go here. Just start this one first. Okay, like that. This positive zone can be attracted to this negative zone, or it can also be attracted to this negative zone. But this will not be like this will unlikely to be attracted to this negative zone, because this is still in refractory period. Yeah, refractory period cannot be attracted. So the only way that it can go is in this direction. Yeah, it can only be this is what they call active. From an active zone to a resting, active region to resting region. So that's the word, yeah, that they use. So this is active region to resting region. So it can only go in this direction. This is refractory period. This is not resting region. Okay, so the direction is only in this direction. So action potential will move from an active region, this is active because it's positive, to a resting region. It cannot go backwards because this is still in refractory period. This is not resting region, this is refractory period. Okay, so it will only go in that direction. So refractive period means the sodium channels cannot open, and this inside cannot be made positive. So this is not resting region, this is refractory period. Okay, so it's not this is a refractory period. Okay, not region, refractory period. And so it will only travel in one direction. Okay, as you can see here, pass only in one direction along an axon. They can only pass from an active region to a resting region. They cannot double back. Double back means going backwards. Double back means going backwards. Yeah. Because the membrane immediately behind the active region is in refractive period and cannot be depolarized again. So there are two important things about a refractive period. It limits the number of impulse. It limits the number of frequency of. It limits the number of the number of frequency per unit time. It limits the number of nerve impulses that can be fired per unit time. Yeah, this one. Yeah, it limits the number of nerve impulses that can pass along an axon in a given time. So this is another name for this is frequency. Frequency means number of nerve impulse per unit time. Yeah, frequency is number of nerve impulse per unit time, and it limits that. That's the purpose of the refractory period. Yeah, and then it only allows one direction from an active region to a resting region. Okay, absolute and relative refractive period. This is no longer in the syllabus, so I'm not going to talk about that. It's not mentioned in the syllabus about the relative and the absolute, but I will also explain it tomorrow. Just going to touch it very, very briefly on absolute and relative. Right, that's all for today. I'll see you again tomorrow.